Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 9. We would just like to recap what we have done so far. We learnt about crystal imperfections. We also talked about point defects, for example the the different kind of crystal imperfections like point defects, line defects, surface defects, etc. We also discussed about the elastic and plastic deformation from an atomistic point of view by understanding a 2-atom system. We further considered the model for understanding shear yield stress and found out that really depends on the dislocation what is going to be the ultimate shear yield stress. Then talked about hardness, ductility, toughness, some of these parameters, and also discussed in details about how do you do the tensile testing for mild steel and some other metals, where we did models, or we tried to just understand models where the behavior of the metal could be an idealized rigid plastic behavior or idealized elastic plastic behavior, or as a matter of fact elastic linear strain hardened behavior, so on and so forth. Today we are going to look at another very important property which is related to all the machining, which is called friction and wear. Okay. So it is well known that whenever a solid surface slides over another, a resistance force commonly referred to as a friction force develops. The friction phenomena was studied for the first time by Amundsen and Coulomb. Let us consider these two surfaces, for example A and B, in contact as in the figure below. So though a surface may appear smooth in plane, really it is not so. It is there is no surface which can be recorded as being perfectly smooth. There are going to be asperities in the surface, and when these asperities touch each other, there are going to be some shear deformation, because obviously the area of contact which happens because of an asperity touching an asperity of two surfaces which are mating each other are going to be very, very small, and so therefore the overall plastic state of stress is attained very fast because of the small area. Stress level goes very high, and you can think of it that as the plastic stress happens, there is some kind of a cold weld which develops between both the materials, and in the process of it the area increases. Okay, the area of contact increases. So these small asperities would have a smaller area, but as the plastic flow starts, really the interfacial area between the two asperities which have mated, they would start to increase because of the plastic deformation. Okay. So these kind of build up the cold welds, and these cold welds, when you want to remove or sort of move one material over the other, would have to be broken down in order for the material to have a relative movement with each other on that interface, and that is what really is friction. So in a nutshell, if we assume a rigid plastic material and if sigma is the ultimate yield stress in compression of, I can say, the weaker material, because obviously if the materials are same, then there is no problem because they are going to be the same yield stresses. But supposing there is a generic model of two different materials sliding over each other, then obviously the weaker material would be the one which would be talking about in terms of the yield stress of compression which would be achieved. So of the weaker material, so obviously the stronger material will try to sort of affect more by deforming more the weaker material. Okay. So then the real area of contact all over the mating surfaces can be expressed as A real, which is equal to the normal force n by the sigma of the weaker material. So, that is how you can calculate or back calculate the real area at a certain instance of time. Okay. And you can assume that this particular sigma is the already reached ultimate yield strength of the weaker material, assuming that the weaker starts deforming faster, obviously because the harder material would deform the weaker material. And already this critical limit y has been reached, beyond which the weaker material goes into the plastic flow straight. Okay. So, that is how the real area can be calculated. So, large stresses and plastic deformation cause the upper contamination layers to tear off, and the real material comes in contact so there is local welding. So, in order to move one surface with respect to the other, these local welds have to be sheared, which is really what the friction force would be. So, here if we consider that tau is the yield shear stress of the weaker material, then the force required to shear off a junction with a total area, and let us call it interfacial area, because this is what the post welded situation is, a real, let us suppose, is F equals tau times of a real. Okay. So, this shearing force is the force of friction, as we have already earlier illustrated, and obviously we define this coefficient, which is a ratio between F and N, which is nothing but the tau times of a real divided by sigma times of a real. So, it is basically the ratio between the ultimate shear stress to the ultimate tensile stress of the weaker material. Okay. So, that is how you understand friction. So, the model is valid only when the real area of contact is much smaller than the apparent area of contact, and if the normal load n is gradually increased, the aerial increases and approaches the apparent area of contact, and aerial once reaching a value equal to A, the shear force does not increase any further, even if the normal force n is increased. And such a situation, there would be many other mechanisms which will come into play, like interlocking of the asperities, and maybe the local welds among those interlockings, which would actually result in a lot more different condition and lot more unpredictable behavior in comparison to till and until this phenomena of aspirity welding or this physics of asperity welding is obeyed. Okay. So, if I really look at the variation of the normal force, for a normal force corresponding to the force beyond which the apparent area would go higher than aerial, the frictional behavior is completely bizarre. Okay. And till and until you can have a situation of asperity welding and shear deformation of the welding, this kind of a limit, the friction obeys the normal Coulomb's law of F equal to mu times of normal reaction n. So, that is how friction can be studied. Let us look at wear. So, wear is something which is when a solid slides over another, obviously the surfaces would be subjected to a gradual loss of the material. So, wear is a post friction phenomena, where when we want to dislocate the, or when we want to shear the local welds, in the process of doing that, obviously there would be a breakage of the weaker material for the flowing of the top portion or the stronger material over the weaker material. Okay. So, if there is a breakage and if there is a chunking action on the top of the weaker material because of the continuous shear force, automatically the material loss would be there from the surface of the weaker material, which we also known as wear. So, a fraction of the material lost from one surface may be transferred to the other body, for example, as we saw in the case of friction, or it may just be dislodged into the medium because there is a sort of a brittle fracture and a chipping action which happens. So, if the process is a gradual loss, then you can call it frictional wear. So, there are many mechanisms in which wear can take place. Abrasion is one of the mechanisms in which one of the surfaces contain very hard particles and dislodge the material from the surface in contact during sliding by ploughing action. For example, you can look at what happens when you use emery paper or sandpaper, of different grades. So, there are many abrasive particles which are adhering to this paper, and once you are ploughing these the adhesive particles or the abrasive particles into the softer material, it is going to break and damage and embrittle the material and take away a lot of the material this way. So, you dislodge some of the material from the softer material surface, and so we call that the softer material is being weared because of that. So, that is abrasion, okay, because of hard particles being adhesively bonded to one surface, dislodging the other softer surface over which this surface is being rubbed. The other mechanism is adhesion. When the bodies come in contact are of similar nature, the asperities on the contacting surface tend to get welded, and sliding in such a situation would cause fracture of these welded junctions and material is lost in both the surfaces. So, you can call it frictional wear or adhesional wear. And there is a third type of wear which would happen because of a presence of a diffusion gradient. Say for example, if there is, let us say, atoms in metallic crystals always which are present in some concentration distribution. So, always there will be a movement from a region of high concentration to that of the lower concentration. So, there is going to be a dc by dx set up between both the surfaces, because of which the higher concentrating or higher concentration metals would move towards, or higher concentration of the metal would kind of balance by moving into a lower concentration region, but that is actually a mass transfer or a mass transport and would be recorded as wear. So, when two dissimilar bodies slide over each other, the atoms of various constituent elements diffuse across the junction just by this dc by dx concentration gradient. So, this can lead to the wear. So, basically you have three different mechanisms which we have discussed. One is abrasion, where there is a set of abrasive particles hard enough bonded to a surface trying to dislodge physically. Another is adhesion, where there is a, let us say, weaker harder material in contact, where there is a asperity locking or asperity welding, and then you have a forced shear. So, that material from the softer surface comes off. And third is diffusion, where there are two different kind of concentrations of a single material, which is allowing the dc by dx to promote the mass transport of the material from the softer surface to the harder surface and so on and so forth. So, that is where let us now look at metals and alloys, because we are going to do castings etc. in the later modules, and we need to understand some of these two phase or multi-phase materials, how they are made. So, you know that various materials used in engineering today, they include metals, they include alloys, ceramics, polymers, so on and so forth. Alloys are a major component of the engineering material because of their increased or enhanced property, because of the various properties brought in by two or more participating metal atoms. So, in engineering applications, metals are hardly used in their pure form, and there is always a issue about using suitably alloyed materials, so that increased engineering properties can happen. How do we formulate the alloys is a big question, and for that we need to decipher something called solid solutions, which is basically something like it has the same model as liquid. In a liquid solution, you have something which is a dissolver, and then there is a solute, right. So, the dissolver is also known as the solvent, which is in larger quantity, in bulk quantity, and the solute is probably in smaller quantity, and you put the solute inside the solvent and dissolve the solvent along with it. In the same manner, an alloy can be defined as a mixture of two or more materials, of which at least one must be a metal. So, in case of, for example, steel, as you know, the other phase, which is the solute in that case, is carbon, okay, and it is less than 2% carbon, which makes or qualifies it to be steel. The other part is of course the liquid metal, which is the iron, okay. So, the material having the largest percentage composition is typically known as the solvent, and the remaining are solutes. So, in iron carbon case, carbon is the solute, iron is the solvent, and such a mixture is often known as a solid solution. So, only difference here is that at room temperature this would no longer remain liquid, and they would freeze up, and they would formulate organized polycrystalline structure, which is the difference in this particular case. In the case of solutions, you have the luxury of having them in liquid state in the room temperature itself, okay. So, you can predict their behavior much more easily, but if once it is solidified and there is complete stoppage of all the movements over and above what the dislocations carry forward, it becomes very difficult, and it becomes you have to treat it as one sort of fixed structure or static structure, unless there are some other associated processes which come up. So, when site of the solute atoms is small enough so that they can occupy the interstitial spaces of the solvent matrix, the solid solution is of interstitial type. So, you can see here these are the interstitially occupying spaces, and if supposing the solute atoms are large, so that they have to displace actually the atoms from the crystal and occupy their position, they are called substitutional type. So, in this case there are smaller, let us say carbon for example is much smaller. So, they have a tendency of getting into the interstaces or the voids between the metal atoms in the crystal structure, and in case the metal is too big, it has to substitute the parent metal in order to get into the crystal structure. So, you can categorize them as interstitial and substitutional. So, for normal metals, the only useful material which can be accommodated in interstices is carbon, as you have seen in the steel, and I am going to do a lot of detailing in this area. And some other types of solid solutions is formed when the solute atom occupies regular matrix position. So, such a solution is known as substitutional solid solution. So, I would like to now sort of go ahead and close on this particular module, but in the next module we will learn about details about these solid solutions and how they behave on the temperature scale as a function of temperature and their transformation in time. Thank you so much.